The other particular is that the messages to the kids to get you that one particular switch will happen. Where the no longer the flip will never arrive on that. There's conditions. So let's say there's suggestion for this switch, but there is no condition for this switch. So they are all in the same traffic. Because even if this on the place, there is no conditions, they can have all. Processes. They should have in phase of the SM is the what's the problem that you want to have something and then you have the way yes and you said everyone said each tree is built up out of all those splits. Tree can build up and reverse. Why so like one socket can have all
Okay. Let's start with a few announcements. One second, sorry. My Zoom is set up right. Which way do I have to go? Where are you, screen? No, no.
You have multiple songs, say one CPU.
Okay. Sure. Sorry, this is taking so long. All right, so a couple of announcements if you're not following on Piazza, which I recommend that you do. So I've set the final exam date. It's a little bit later than it said originally on Brightspace for a couple of reasons. Wanted to give you guys a bit more time because that week that it had been set for is actually kind of we'll do it on basically the last week of class. Okay, and we'll just do it in class, so you won't have to take any special, night exam or anything. So it'll be an hour and a half long. And I'll post last year's exam, which had a similar format to Piazza, probably hopefully today, if not tomorrow. The content on the exam is basically going to be everything up until this slide deck that I'm covering today. Okay, so part of the exam is going to be on CUDA. Just give you some CUDA. You don't have to code. I'm not going to ask you to code up CUDA. I'm not going to mark code. But I will give you code samples and ask you questions about it, see if you can understand and analyze what it's doing related to GPU specific stuff. And you'll see some flavors of this on the previous exam. And that'll be, the CUDA part will be roughly 40% of the exam, 35, 40%. And then the rest of it will be on the architecture stuff. Again, those will be kind of conceptual questions. We'll talk about some of the mechanisms we studied in this class. You have to answer, some questions on how they work, on what happens as you sort of scale things and change things around. If you've ever taken an architecture class here at Purdue, you can expect some flavor of chocolate computer type question, right? Where it's like open-ended, but there's only really one way you can go. But it'll be related to GPUs. Okay, it's not obviously it's not going to be like a chocolate CPU, it's a chocolate GPU. And then some sort of basics on like, do you understand how the hardware works? Are you able to, comprehend the sort of mechanisms we talked about? I will let you, because I'm a super nice guy, bring in your own note sheets so you don't have to memorize a bunch of stuff. What I won't let you do is just photocopy your friends or just like, take the slides, paste them into a PDF, and then print it out and bring it. Okay. Part of the exercise of like, so I want you to study. Sometimes students don't study very well, at least from the exams. It looks like they have to study. And so if you have to make a note sheet, then it sort of forces you to like go through the material and like parse it through your head and condense it into something that you write down on a piece of paper, right? And I think that's usually a valuable exercise because some of that stuff that flows through actually sticks in there. And if you do a good job making your note sheet, you don't ever have to look at it. I remember when people used to let me do this. Whenever I did a good job, I never needed the note sheet. I'd like spend hours making this note sheet. It'd be beautiful. And then like I never actually referred to it because I spent so long making it that I just knew what was on the sheet anyway. And the things I got wrong were stuff I didn't do on the sheet. Or I never got anything wrong. Yeah. So anyway, I think this exercise of creating this note sheet sort of is helpful. But again, don't just, if you show up here, and I've had students do this in the past, show up with just a photocopied thing or a photocopied handwritten thing, trying to say that it's not photocopied, like, don't do that, please. You cannot bring a note sheet, or you can bring a poor note sheet. I don't care, but don't try and just leverage your friend or leverage the guy who did it last year and take their handwritten note sheet. Okay, don't do those things. On the front of the exam, you're going to sign to say that you wrote the note sheet yourself. It's meant to come from you, not to come from someone else. Okay. Obviously, if your friend wrote it and they gave it to you, I'm not going to go into forensic hand analysis, right? It's not my job, but you will be cheating yourself and cheating the class. That's between you and God. I don't know. There's nothing I can do about this. But it does have to be handwritten. Okay. And that's sort of the intent. Questions on the exam? All right. Okay. Generally, people actually do pretty okay on this. It's usually not, I don't try to make it especially hard. And there's also opportunities for bonus in your programming assignments, et cetera. Some students will just be like, I don't care about the exam because you make it all up in bonus. And to some extent that's true, but don't do that, please. I would like you to, I do look at the exam scores on like, okay, who really learned stuff in this class? And when people come to me for letters, I don't just look at the letter they get in the grade, right? If you want a reference letter for a company, I go back to the exam and I say, how did they do in the exam? Okay. So even if you pull off an A+ and you tank the exam, then it's like, well, they worked hard, but they didn't really understand the material super well, right? So it is important to do well in the exam. All right. Let's go to the next slide deck. So we spent a couple of lectures just talking about DRAM in general. And then I have this now older, almost 10 years old, unfortunately, slide deck from one of the research scientists at NVIDIA who works in their DRAM division, or in the DRAM, to try and figure out what they should do about DRAM. And then he created this slide deck that I've leveraged for a couple of years now on, what is different about DRAM for GPUs. And so this deck is basically theirs. So this is sort of the trend line of DRAM and GPUs. So GPUs don't use DDR. Okay, the traditional DDR4, DDR5, they have never used it since their inception. They have a special kind of memory called graphics DDR. And in the same way that DDR has been numbered, right? DDR2, 3, 4. Contemporary CPUs are on LPDDR5 or something now is sort of I don't remember what the current CPU technology is. But, again, what are these things? This is just something JEDEC puts out. JEDEC is a standards committee that says this is what, these are the timing characteristics. This is pinout. This is like how you interface with one of these chips. And so graphics has always had its own special interface even before HBM. Okay, so HBM is also used in CPUs now, but GDDR was sort of the high bandwidth alternative to graphics memory, to traditional CPU DDR memory, even back before we had 3D die stacked HBMs, which is what they use now. Okay, so there's been several iterations of this, and what they're showing here on the y-axis is just the gigabytes per second that you get out of each technology. Okay, on different chips. Okay, so every chip will have, when I say chips, I mean, what I mean is GPU cards. Okay, when you buy a GPU, it'll say how much memory bandwidth it has. That's what the y-axis here is, number of gigabytes per second. So back in the sort of time frame of 2008, so GT200, this is the first GPU that ran CUDA. You were, around 250-ish, right, gigabytes per second worth of memory bandwidth. Smaller machine, fewer threads, less memory demand, so less need for a huge amount of memory bandwidth. How did they do it? Well, the interface itself was 512 bits wide, so that is the interface, the data interface to GDDR3. And to figure out data rate of each individual chip, you basically just take the number of pins and the clock rate. Right, you have a number of data pins, and then you're clocking it at some speed, or your effective data rate if you're reading on both the rising and falling edges. And so GDDR3 was 512 bits, and it was at 2.2 gigabits per second. Okay, and then they sort of revved it several times. GDDR4 never really got any uptake in NVIDIA GPUs. They went to GDDR5 for their Fermi chip, and they changed the interface, so the interface got narrower because it's cheaper to have fewer pins. But then they cranked the clock speed, so you still got a little bit better bandwidth. So they're sort of playing games here on like how wide the interface is versus how fast you're clocking it. What's the trade-off between either giving me more bits or clocking fewer bits faster? Yep. Space. So more bits is more space. And power consumption. Faster is going to suck more power. Okay. So and there's games you play here, right? And this is sort of the games that were played in the interfacing technology as they sort of went through these levels. And so, GDDR5 revved a couple times. So it was GDDR5, A or whatever, then B. These are different generations of GPUs. So now we're in the 2013 timeframe. And here they didn't actually make the interface any wider, right? The GDDR spec didn't change, but they just started cranking it faster. Okay, it's still GDDR5, but they started to increase the frequency. GDDR5 still increasing the frequency. And then, this is sort of the end of where the GPUs use GDDR in their high-end parts. In commodity graphics processors, they'll still use GDDR. Okay, they won't use HBM because the bandwidth demands are more set. They're cheaper components. They don't want to have to pay for the HBM memory. So, there will be components that still use GDDR6, 7, but generally the high-end cards, so the V100s, the A100s, the H100s, the Blackwells, these have all moved into some flavor of HBM. And so the big difference with HBM in the first generation, okay, again, we're sort of moving up little bits at a time, but the big sort of massive difference between traditional GDDR and HBM is just the width. Okay, HBM goes way wider. Does anyone have a guess on why they can go so wide? They stack it, right? And traditional DRAM is planar. Okay, GDDR is, you basically have, just one level of memory and then a bunch of wires on top of it. HBM is different. It is a practical implementation of 3D die stack technology. So you actually have one layer, some metal, and another, and another, and another, and you can stack up all of these layers. And then they have things called through silicon vias, because I need to take the signal that's up on the high part of the stack and bring it all the way down to the bottom. And I have many of these through silicon vias coming out on the bottom of this chip to create a huge number of pins. These things called micro bumps. Okay, this is packaging technology. But to an architect, it's like, wow, I get a really wide interface now because I've got all of these little micro bumps here that give me access to this data that's stacked in the HBM chip. And AMD, I think, was actually the first one to use HBM at all. So this was in the 13 timeframe. So they actually had a bandwidth advantage on NVIDIA slightly, and they dropped the frequency. Okay, so you can get the same, more bandwidth because you have way more pins and you drop the frequency and you don't need some like super wide chip interface now because it's all coming out from the bottom of this 3D die stacked substrate and gives you a huge amount of bandwidth. HBM2 sort of takes that and then goes further. And they have different amounts of stacks. So, you can basically, you buy these things like chips and there's stacks of them and then they get put on the PCB. If you've got 4 of these stacks with HBM, you crank them at 2 gigabits per second. Now we're starting to get up into higher data rates. This was a future GPU in 2015. This is probably Volta. Volta was HBM2, right? Who knows this? I should know this, but I don't remember. I think Volta went to HBM2. And then now they're at HBM, whatever, 3. So this was saying future DRAM, it still needs to scale. And, this presentation was sort of focused on how do we get to an exascale node? So a node that can do like an exaflop operations per second. And we need DRAM to continue to keep scaling its bandwidth, okay? Now, to give you some context on what a typical CPU has, like a typical PC CPU or your laptop is somewhere around here, right? It's 500 gigabytes per second. And it's not because CPUs suck, they just don't have that many threads, right? There's just not that much demand. I could give it a big HBM system, it'd cost way more, and it wouldn't ever use the bandwidth because you don't generate enough misses in your last level cache because there's not enough concurrent work happening to really justify it. So typical CPUs are here. If you have a high-end CPU, like one of these server CPUs, that will have 80 threads on it, and it will be generating enough memory traffic to justify putting HBM in it. You're up around 100 gigabytes per second. But typical GPUs today, like I don't know what the Blackwell. Does anyone know what the Blackwell number was on bandwidth? They're in the thousands of gigabytes per second.
I think it was like 2 terabytes.
2 terabytes per second memory bandwidth. It might be that high because they have that many channels, right? If you just scale out the number of memory channels, it gets higher and higher. Okay. So why did they need so much bandwidth? You guys know this. It's because there's a lot of threads in the system. And what's more is that the memory hierarchy of a GPU, this is Maxwell, but these trends have sort of stayed true even in the upper Blackwell, the newer generations, is inverted versus the CPU memory hierarchy. Right? This thing on your right is what you expect from a memory hierarchy. If you take 565 and 666, you've got a little bit of space for physical register file. Like this is all the stuff that's getting renamed, right? So you have architectural register file and physical register file. That's the actual SRAM for the registers. That's kilobytes worth of data because you've only got so many things you can rename and only so many threads on each core. And your L1 is a few tens of kilobytes, maybe hundreds of kilobytes. L2 is a bit bigger, and then L3 is where they dump all the excess SRAM, right? And that is the biggest, the sort of biggest memory space on the chip. Okay, that's sort of the way you think about it. But in a GPU, the opposite is true for the most part, because you have a huge amount of register file. Why do I need so much register file in a GPU?
256.
No. So many contexts, right? This PRF on a CPU core is handling, maybe 4 threads if there's hyperthreading, maybe 8 threads. The register file on even the Maxwell GPU, from a thread perspective, is handling, 2,000, 4,000 threads on a modern system. Okay, so you need way more register space to basically store the context. The alternative is that you context switch, right? So you have to dump all the registers. What happens in an operating system when you switch out a process, it has to dump the registers to memory, but that is impractical in GPUs. Because there's a lot of state related with dumping stuff. There's, all the register file for all the threads you need to dump. And, that is a high latency process. And all of the sort of fine-grained multi-threading that happens relies on having all the register state be persistent. So you have a huge amount of register file. Then you've got, and again, these are aggregate numbers, right? This number isn't, and it's aggregate in both, right? So this is sort of like per core this is added up among all the cores, right? In the CPU, if you've got like a reasonable amount of CPU, this is all the L1s. If you've got like an 8-chip multiprocessor or something, this is all the register files. This is all of the L1 and scratch pads. So you've actually got megabytes of this spread among all of the different SMs that you've got. And then you've got this little itty bitty L2 compared to everything else. Again, there's only one of the L2 shared across all of these cores, whereas you have many of these cores that each have some small component of each of these things, right? And many threads. Now, if I take these numbers and then I divide them out by per thread ratio, it gets even worse and even weirder, right? If I think about how much storage I have per thread a CPU. So let's say I had an 8-core, that's an 8-thread Intel Core i7, so everything's 8 times bigger. So if I just divide all those numbers by 8, this is what's left for each thread. You know, this is what you're sort of used to seeing within a CPU core, tens of Ks per L1. But if I divide even the Maxwell, which had 49,000 threads, like I end up with like 128 bytes, not kilobytes, of register file per thread, 48 bytes of L1, so not even a whole cache line of the L1 per thread, and 64 bytes, so half a cache line per thread in the L2. So I am severely on-chip capacity constrained versus the number of threads I'm potentially running on the machine. Which means what? When I'm talking about DRAM, I'm going to miss a hell of a lot, right? Because in a CPU, if I can keep working sets inside this thing in a thread, I'm happy. And that's what most of CPU optimizations are trying to do, trying to keep yourself inside the cache. And there's no chance that I'm going to keep all of my accesses inside this like very, very small amount of space. And even in modern machines, these ratios have gotten a little bit larger, but not much, because even if we scale beyond chip SRAM, we keep tossing more threads in there because we want to exploit the concurrency that we could potentially have. So you're going to demand a lot more from bandwidth. You're not going to have a deep cache hierarchy per thread that's going to save you, even if you have working sets that are reasonable. Questions on this? Okay. Right. So basically, yeah, if you add up all the on-chip storage, like I take all these levels and I add it up to just give you everything that's on chip, you have 240 bytes in the aggregate between your register file, your L1, your shared memory, and your L2 per thread on a GPU, whereas you've got, a megabyte per thread on a CPU. So, there's no chance that you're going to capture a huge amount of locality very easily, just on a per thread basis. So you need way more, so that's why they're sort of designed this way. You need way more bandwidth. The other upside, the thing that we can leverage here is that they're much less sensitive to latency. So if there is a miss, I can cover it, right? I do the fine-grained multi-threading to try to just schedule more work underneath the miss. So I don't really care about how long the memory accesses are, or at least to a point. So something like DDR memory or LPDDR is much more optimized for latency. A single round trip per request needs to come back quick, because when I miss in that last level cache, that single thread is filling up your ROB. It's, spinning, waiting for that thing to come back. You need to make sure that that comes back quickly. Okay. In the GPU, we don't really care quite so much about how long it takes, because we're assuming that we have other work. Now you've got to have enough pins, you got to have enough bandwidth that like I can keep missing and keep like going to get stuff, but we're much less sensitive to this latency. And this talk at least tries to make the argument, certainly on general workloads, that the access patterns are actually much less regular in GPU memory than they are in CPU memory. This maybe isn't so true today with these very optimized machine learning workloads that have been tuned very, very specifically to try to make the accesses extremely regular. But if your CUDA programs, the things you wrote in the first part of this class, are going to be actually less regular at the memory system than you might expect. Okay. And there's good reason for this. So, okay, so this less regular thing, I think this guy really likes South Park. So do you know who this guy is? South Park, nobody knows this anymore, right? Okay, try. This is not Kyle. Butters. Thank you. This is Butters. Anyway, if you don't watch South Park, I don't actually recommend that you start. You're probably too old now. But anyway, so he's persistent here for some reason. So, okay. So I said less regular. How? Right? Like if I wrote my program well, you did everything I told you to in the first part of the class, and you made nice coalesced accesses, I should get big sort of chunks of 128 bytes demanded by all of the threads, right? If I just do this, linear offset by thread ID on my load, right? Something plus thread ID without any multiplier on the thread ID is just going to create a nice coalesced load, okay? So that's good. But the problem is that all of these SMs and all of the warps on the SMs are all happening in parallel, and they're all multi-threading between each other. So you've got 100 SMs, and yes, maybe each of your individual warps is nice and coalesced, but now I've got 100 different, warps at any given cycle, potentially going to my wide DRAM system. And then on the next cycle, I've got another warp from that same SM going to that same DRAM system. So I have a huge number of warps that are getting interleaved in a somewhat arbitrary way because, it just depends on, when it gets to the memory access first. Typically in a program, if they're all sort of going at the same rate and the clocks are, the same, they'll all get to the load at the same time, right? And then you'll sort of have to arbitrate between them all. And then some of them will come back early and they'll be able to make a little bit more progress. Some of them might hit in the L2. It's just kind of a huge mess of a whole bunch of warps operating at the same time. So even though you had that sort of nice, even memory access in each warp, on this is Maxwell, so this is much smaller. So it only had 24 SMs. Now you've got like 100 and something SMs, each of which has 64 warps, each of which is being interleaved, across the warps on a cycle by cycle basis. Now you're not going to get this nice striding access pattern that you had in your head when you wrote that coalesced code. From the perspective of the memory controller, it's a god-awful mess. Okay, you're getting accesses from all over the place. And then all of a sudden, things that you think should work well in the memory system don't work super well because the cores themselves are not tightly coordinated. They're running off in whatever direction makes them the most fastest, which means that you'll end up with like stuff that you'll end up with a few side effects. One side effect of this is that we're going to have a lot more bank conflicts in the GPU memory system, despite having a lot more banks. And again, a lot of this is due to the fact that the number of threads does not scale with the number of memory elements. Even though there's way more bandwidth, I still am not scaling the number of banks, for example, at the same rate that I'm scaling the number of threads. So let's take a CPU. It's got 8 threads. And let's say I have a memory system that has 2 ranks in each channel, and then I have 8 banks in each rank. So that means on average, I have about 4 banks per thread. Okay. So that means that, each thread sort of have 4 banks like to play in before it actually has to incur bank conflicts and slow down the memory system. When I take a GPU, and this is a realistic number from a real machine, and this is the number of warps that are running. So again, I've smashed down the number of threads to warps, assuming that you've actually got good coalesced access, and each warp is just giving me one thing. Okay, so this is with coalesced accesses. I've got 36 warps running now. So 36 different memory accesses potentially on any given cycle. And I have a wide memory system. I have many channels. In the case of the Maxwell, it was 6 channels, and I have 16 banks per channel, but that did not scale. The number of banks did not scale with the number of threads. So the number of banks per warp that I have is less than 1/10. It's 0.06. And that's assuming you've got coalesced accesses. If you have uncoalesced accesses, it's game over. The number gets multiplied by 32 because now they're like spraying all over the place. So that means that my ratio of bank conflicts is going to go way up versus the ratio of bank conflicts I had in a nice CPU memory system that every thread had 4 banks to play with. And so this was actually measured on, and so energy is another factor here. So they measured, this is across like x-axis here is applications. When you look at data that's published from industry, sometimes they don't actually put all the application names on there because they can't tell you what it is. So they just have these like amorphous x-axes, and then they do this thing called S-curving it, where they just sort it. But every data point on that blue line is basically an application. Okay, so some workload, and then the y-axis is the number of accesses per activate. So once I activate a row, how many accesses come to that row at a granularity of 32 bytes, because that's what the memory system in this example is showing. And so what that says is, when I open a row, how many times can I leverage that open row before I have to close it and move to the next one based on the memory schedule I see? And the average here, that's what the red line is 5. Okay, so that means that I can get 5 accesses to a 32-byte quantum on average across all these workloads before I have to close that row. And the rows are very wide. So we'll quantify that in a second. But this is also very application dependent. So very simple things like graphics rendering. So inside companies, they have access to all the games or whatever. I think this is Angry Birds, I guess, right? So this is some 2-dimensional flash render or whatever Angry Birds is written in. Like this actually behaves pretty well. This graphics has a very regular access pattern. And once you open a row, you can tend to utilize that open row very well in composing things like images. And then graphs are just an absolute disaster. You go down to 1. because graphs are hard for every processor, and on GPUs they're especially hard because it's sort of like I go to one node and then I have to go to the next one. And I have no idea where that is until I go to it. So you're reading these non-contiguous chunks of data. So you end up with just sort of a disaster in the memory system. You open up this super wide row and then you read like one pointer to get to the next, location, and then you go there and you open up this super wide row and read one pointer. So you're just wasting a ton of energy. And then of course, those are the two extremes. And then of course there's stuff sort of in between. Now, today with machine learning workloads, they're probably, they play all kinds of tricks to try to tend them this way because this is important, right? Trying to make sure you use the row, but it's if you've got these sort of this fine-grained interleaving happening in the processor. As long as you're doing multi-threading with multiple cores, trying to orchestrate sort of perfectly linear accesses across many threads is very hard to do. So in some ways, the GPUs may not be the absolute best architecture for doing things like machine learning matrix models that are very, very regular if they have all this multi-threading that adds all this uncertainty in the memory system. This is probably something that's going to be addressed in the future to try and help GPUs stay ahead of all of the machine learning accelerators that are coming out. Questions on this? All right. Next piece. So Gddr. So we've talked about DRAM in general and sort of focused on the CPU side. So what is different about graphics memory? So let's start with Gddr. What am I doing? Actually, this is not Gddr yet. Okay. Pretend that this slide isn't here and it's actually 2 slides from now. So let's talk about energy first. So what I said was that, that graph I showed you on the previous slide, I should fix these slides. The graph I showed you here is the number of accesses per activate. So what is the ramification of this? It's bad for energy, right? So DRAM typically has at the HBM and GDR level, each row is about 1 to 2 kilobytes worth of data. So every time you activate a row, you get 1 to 2 kilobytes worth of data. And on average, we're only reading about 160 bytes of that 1 to 2 kilobytes. So you light up 2K worth of sense centers, and you actually use about 160 bytes worth of it. Roughly a little more than a cache line, right? So you have one nice coalesced cache line access from one SM. You read all of that. Maybe you get lucky and there's some other stuff on that row, but then there's another access that requires you to open up another row that came from another thread that was not sort of controlled in this very tightly way. So that's a huge waste of energy. 84 to 92% of energy is wasted on this activate and pre-charge of the bank as you try to close and open up new rows. And then if you have a whole bunch of devices in parallel that are all doing, then that makes this even worse. What does it mean for performance? You will end up with a so how do I tune this to try to make performance better, right? You actually want to try and tune the numbers in the DRAM spec to try to allow you to open up more rows more quickly. Okay, so TRDD, this is time it takes between row accesses, right? So if you can lower this in the DRAM spec, this will help with trying to close and open up new rows very quickly. And then obviously have a high number of channels because you need to be able to do many of these in flight to keep everything busy. This is typical for a CPU. These are just some typical numbers to give you a sense of the timing on some of these systems. You're not expected to memorize this, but just to sort of contrast the two. So you've got a typical 2-channel DDR4 that's got 2 ranks. The effective time to move between rows is about 5.25 nanoseconds. And if you just do the math on the number of activations you can get per second across all of the banks in that memory system, you get about 762 million activations per second. Okay, so in a CPU, if you operate this thing sort of as quickly as you can, switching between rows, you can activate about a little bit less than 1K or 1 gig activations per second. In contrast, an HBM system that has 64 channels, that something like that you might run on a GPU that has 4 stacks. There's this thing called pseudo channels, which basically gives you, another channel, right? In each individual channel, I'll talk a little bit about that later. Then the effective RDD ends up being 4 nanoseconds, and you have a really wide memory system. So you can get way more activations per second. So the bottom line in this slide is that as you make the memory system more parallel and try and decrease some of these timing numbers, you can light up more rows every second, which allows you to, basically get more activations and get more bandwidth. If you try to do this with a more narrow memory system like a CPU, you wouldn't be able to light up enough rows to really keep the application busy, a GPU application busy. The other thing that DRAM has is relatively small atoms. So atom is the minimum size that you're going to get back from the chip. Okay, the smallest indivisible access, which is basically a function of the bus width and the burst length. Okay, so you've learned about flits, right? If you're taking 666, you may have multiple flits with each burst, but what is the minimum that I'm going to get back from any device if I've got, based on its specification. GPUs, we actually want this to be relatively small because of this, poor spatial locality. If we have super wide atom sizes, this is going to be bad. Now, the original impetus of GPU memory systems, so graphics Gddr, it comes from the graphics world, right? Like Gddr was invented to sell GPUs for 3D rendering. And we've learned a little bit about this, right? The whole thing is sort of composed of triangles, and you've sort of got these compressed data structures that are your textures that you're constantly accessing. And so, you ended up, I don't know what this diagram is really meant to show you. I think it's meant to show you, like, if you want to render this triangle and there's different textures, right? You're sort of grabbing these 4 pixels, or you're sort of grabbing, to render these pixels, you have to grab sort of different pieces of the image. The bottom line is that the triangles themselves are pretty small, so the atom size you want to go to memory with is pretty small, and they're additionally compressed. So it sort of drives a small atom size just to do the graphics rendering. And there's this magic number 4 in all GPU designs, because why do I need 4 when I think about textures? Why is 4 a magic number when I'm going to memory? RGB alpha, that is true, but what I'm talking about is 4 RGB alpha values potentially.
3 vertices.
Nope. 4 is not 3. Bitmaps. You guys remember bitmaps? Right? I am trying to figure out what the color should be in between 2 planes. I have to project that point to those 2 planes, and I never sort of perfectly fall on one place. I need to grab 4 colors from one plane, 4 colors from another, and blend them. So you're always going to stuff in groups of 4. That they usually build everything very much around needing to load 4 values. Okay. So small burst sizes, so on the order of like 16 to 32 bytes, modern systems are at 32 bytes. And again, you don't really care about latency. You don't really care about extremely large capacities either. Now, this is changing today, especially as we scale up AI, but historically, you could trade off having a big capacity memory for a higher bandwidth memory because, graphics didn't need terabytes of data to render a scene. You'd never be able to render at the frame rate. So that means that we can design the memory technology to not necessarily scale out very well. And that's specifically what's happening with HBM, right? The maximum size HBM system you can buy is like 100 gigabytes. Blackwell's what? I can't remember what Blackwell is. That's not out yet, but it's like 80 gigabytes is the biggest hopper you can get in terms of capacity. CPUs is way bigger, right? You plug a bunch of DIMMs in there, you get terabytes worth of memory on one CPU node. So historically, to get this sort of high bandwidth, we've sacrificed latency, so it's okay if it takes a longer amount of time, and we've sacrificed capacity scaling because it wasn't really necessary. In the future, this capacity thing is a huge problem. Companies are buying GPUs today, not for the SMs, but for the HBM, because they need to spray these giant models across multiple HBM memories, and they don't fit on one GPU. You have enough compute resources to actually compute that memory, but you don't need the compute. What you need is more HBM. So you buy a whole bunch of GPUs and sort of spray your model across those GPUs, and the individual compute utilization of each one goes down. So you're sort of wasting all of those SM cores, but you need it because you need the aggregate capacity of those sort of high bandwidth NVLink stuff that's happening in these modern systems. So capacity is a challenge of the next decade. How do we scale this effectively as machine learning models scale up? But historically, it is this way because we've been able to just say, forget about capacity. Like We don't really need that much capacity for a lot of these workloads, but now we do. And again, we're not also concerned with lowest possible cost. If you ever bought a CPU, you can tell that they're not concerned about making it cheap, right? DRAM is a dog-eat-dog low margin business, okay? These companies that make DRAM, they're all competing against each other for razor thin margins on the product. And, that's what drives the sort of traditional DDR market. Huge capacities at lowest possible cost per bit. Micron, Samsung, SK Hynix, all of these guys, like they're in that game of like extreme commoditization. Thankfully, GPUs just don't care because people will pay whatever you charge. And we're not concerned if the memory is actually kind of expensive. As long as we can make enough of it, we should be okay. So they're not optimized for cost. Okay, doing the HBM stack thing is actually kind of expensive, right? Versus the planar technology. You can get way better bit per dollar if you planar tech versus HBM, but it doesn't matter because who cares? People are going to pay it anyway. Okay, so my approach to do this is high-speed signaling. So you start with sort of a traditional DRAM core. The GPU doesn't need a huge capacity, so maybe we don't have multi-rank support, so you don't have all these DIMMs you plug in for maybe getting multiple ranks. So we just assume you have one rank or very few ranks. You don't need these, multi-drop buses, sockets, all this push I/O. So when you plug in the DRAM pins, right, into your CPU, all of that is noisy. And that means you cannot crank the frequency on your DRAM as high as you could if you just put it right on the board. So this is why you can't plug in DIMMs on a GPU, because it would slow down the signaling. And we can get a much better data rate if we just, hard tie the DIMMs to the card, which has sort of left us in this situation where when you buy a GPU, that's how much memory it has and that's it, because it's all hardwired into the PCB to make sure you can keep up these high rates of signaling. And the DRAM technology, the Gddr DRAM technology is designed that way. They know that you wouldn't be able to get this kind of signaling rate if you had to push in DIMMs, but they know you can get it on a PCB. So, nobody sells Gddr DIMMs, right? You can't go to Best Buy and buy a Gddr DIMM and shove it into your desktop because you can't meet the standard if you're using these IOs. And we can sort of beef up the DRAM to try to reduce the time. So trying to get that RDD really quick. You can think about the circuitry that's inside the DRAM chip that's attempting to open and close rows. Let's make the drivers bigger. Let's make them try and get the rows open and closed as quickly as possible. We can do that because, again, we don't care about how much it costs to make these DRAM cores. We don't care about the capacity we're losing by putting these extra circuitry components in here because we can get good margins and because what we really care about is just making sure the bandwidth is high. And that is sort of what GDDR is, okay? So if you look at a GPU, this is a core, like this little piece on this is the actual SMs themselves, and then all of these are the DRAM chips. And this is a core that has graphics DDR on it. And the signaling rate is super high, 8 gigabits per second. Right? You're not going to do that on DIMMs plugged into a board. It just keeps moving, right? This was back in 2013. They were at less than 10 gigabits per second. Now as GDDR scales, that's essentially how they scale bandwidth. They keep pushing the signaling rate faster and faster to try to increase the bandwidth. This is tough, right? This is kind of tough to manufacture. Anyone who's done any PCB design, any of our undergrads do PCB design in like their whatever it is, embedded systems 477 or whatever, right? You weren't trying to hit 8 gigabits per second worth of signaling, right? But you can imagine how hard it is to make sure that you design the board so you can actually hit those signaling rates. And the energy is not great because it's all being signaled super fast. So, you're sucking a lot of power that maybe you didn't necessarily need to do if you didn't care about the bandwidth. Okay. So inexpensive boards and packaging are a problem. So things tend to get more expensive. It places a lot of demands on the DRAM core itself to try to make sure that it can maintain these very fast rates of opening and closing stuff. So you need the cores themselves. Like when I say cores, I mean like the stuff, the circuitry inside the DRAM chip that's actually orchestrating all these commands, right? From a memory controller's perspective, you just send it like, give me address this, or refresh this particular row. But that has to come in, get decoded, get actually implemented. Like all of that is actually what we're referring to as the DRAM core here. That is just taking those commands from the memory controller and actually doing those commands on the memory array. To try to get it to hit these aggressive timing rates, it's tricky. Right. Okay. So another approach to try to do this is in-package integration. So this is what 3D die stacking enables. So, when I say in-package, I mean, that little black thing that was on the PCB, right? That's the package, right? That's the sort of final packaged IC. Let's try and just change how we manufacture these things to stuff more bandwidth into them. And HBM is basically a 3D die stack technology. Just like I said, it basically means that we're just taking layers of DRAM, stacking them on top of each other, and having a whole bunch of wires through vias go down through all the layers. This was really hard to do. Like, they talked about doing die stacking for years, right, from a manufacturing perspective. And then in the early noughts, they sort of got it right and were able to mass produce it. And now we have HBM. But the through silicon via thing was very hard to get right from a technology perspective. So now I get a whole bunch more pins, which basically means I'm way wider, right? And now I can slow the clock down. So I can't keep scaling the frequency of a Gddr. So I'm going to have way more pins now and then just scale the frequency down so that way I can get the same or more bandwidth as we go. Questions on this? So that's Gddr, okay? Gddr is really fundamentally the same thing as DDR, except all of these other components within it are optimized to try to get more bandwidth. And you have to put it on, like the signal requirements mean you really need to spend time putting it on the chip. Questions? Yep.
Well, you might answer it in that slide right there, but my question was about, like, since HBM and GDR are like standardized, right?
Yep.
What's the point if they're going to be built into the PCB that NVIDIA is designing themselves?
Because NVIDIA doesn't make the memory chips. Okay. So companies like Samsung and SK Hynix and, well, does Micron actually make the NVIDIA buys? I don't think they do. I think the two major vendors are Samsung and SK Hynix. They build those chips. So that interface is important between those two companies. And again, NVIDIA is like, DRAM, that's a dog-eat-dog business. I'm going to make my high-margin GPU part. I'm going to let the DRAM manufacturers duke it out for bit per dollar. But that's actually turned into a gold mine for them, right? Because NVIDIA will pay a premium because everyone's paying a premium for the GPU. So now, like this factory, this fab that they're building here in town, you maybe heard this on the news, right? The SK Hynix, they're supposed to build a fab. If the Indiana government kicks in a few million or whatever they want, right, then they'll build a fab that will make supposedly HBM chips. Right? They'll be making these chips up on Caldera in like a decade or something. So that's why, because it's separated economically. Good question. Other questions? Okay. So HBM is sort of this, and again, the names are terrible, right? Like in 30 years, when memory is higher, are we going to have very high bandwidth memory? It's like VLSI, right? Like, what is high bandwidth memory? It's like higher than the thing that was before. You should never name something with something this like abstract, right? But marketing people love to do this because when they go talk to like laymen, they're like, "Oh, this is high bandwidth memory." Like, oh, okay. And 20 years from now, the name never ages well. Then you're talking about this slow thing that was high bandwidth memory. Anyway, this is a symptom of like trying to convince people to buy things. But anyway, that's what HBM means, high bandwidth memory. They really should have called it like 3D cube. It would have been a much more like engineering accurate name, but they chose high bandwidth because it's easier to understand. And this is the standard, so it sort of replaces the DDR standard. And this is how not just GPUs, but also HPC systems are being built. Like if you're building a big CPU that has a whole bunch of cores and you want a bunch of memory bandwidth and you're not really as concerned with cost or scalability, or maybe you have an HBM on the circuit board and then you back up to the GDR, like that's your backing store right in your CPU system. So you can sort of treat it like a cache or treat it like a sort of low latency memory system or high bandwidth memory system close to the core. You can do that. In GPUs, this is the only memory, right? If you want to use any other memory, you have to go back to the CPU. So we want to reduce the I/O costs, higher fraction of peak bandwidth. So we want to give the memory controllers more room. So the standard itself handicaps some of the clever things memory controllers can do. Okay. So there are games you can play that are just not allowed to be played in GDDR or DDR because the standard says that those aren't available. So since they were designing this brand new standard, they opened up a few of those games, like concurrent bank accesses and sort of like pseudo channels and kind of, aggressive DRAM architectural things that are enabled with HBM that aren't enabled with the other memory technologies. This is a standard, so you can look this up. And this is public. You can't actually I think you have to sign up for a JDEC account and then ask them for the document, but then they'll mail it to you. And if you really want to know what's going on inside HBM, because I don't know, you want to build an HBM memory controller because you got nothing better to do, you can get the 300-page document and you could go write the Verilog that would interface with an HBM chip, based on the spec. And this has been around for like a decade now, and it keeps iterating as they sort of go deeper. So if you look at the chip, it's actually kind of interesting, right? So this is the GPU, and they're actually wide, right? They're not planar because they have a depth to them that's much deeper than sort of a traditional memory. I have some of these chips in my lab, but I'm not going to rip the covers off any of my HBM chips to bring them in and show them to you. So I'll just show you this picture. It's higher, right? It's not just planar now; it's actually three-dimensional. So what does it mean? So at least the original HBM, and then they sort of iterated on it several times. These things happen in stacks. Okay, so you sort of buy an HBM as a stack. The stack will, by definition, have two channels on it. So they're, just to get one stack, you have two channels built into that stack in each layer. So that means that the stack actually has 8 independent memory channels. Because remember, there's all these pins coming out, right? All of these pins are controlling each of these channels on this stack. So you've got a 4-high stack, so 4 layers, that's the sort of three-dimensional layer is 4, and then each of them logically has 2 channels, all of which have independent pins that sort of come down to the bottom of the HBM so you can interface with them. So this is built for a system that has many memory controllers that can control all of these channels independently to try to soak up bandwidth. So these look like independent mini interfaces. So they have independent clocks and timing, independent commands, independent memory arrays. So nothing happening in one channel affects what happens in the other. And this is in the spec for HBM. Okay. This is not true of traditional DRAM, right? You sort of buy a DRAM chip and you have to put a whole bunch of them together to make one rank, right? This is much different. This is here's a chip. Inside of it, you're getting 8 channels worth of bandwidth. Now, if you want to design a CPU or GPU to, with only one memory controller, you could do that and then just drive the same thing on all these channels, but now you can't have independent operations, right? The chips themselves are able to provide these independent operations, but you have to build a memory controller to actually do it. There's several memory controllers to do it. All right, so what are the nuts and bolts of HBM? One, each individual channel is providing 128 bits of data, and the original HBM gigabit per second signaling rate, and it's basically a 500 megahertz clock that's using both edges of the clock. HBM2 doubles the signaling rate. So again, that means that if you want to build an HBM2 chip, it's got to be able to signal at twice the speed now. A lot of these increments and these numbers aren't really all that exciting, right? It usually just means a higher frequency, right? Or more, that's really usually what it boils down to. And then some of the timing numbers change as a result. So then if you sort of did this multiplication, it works out to 16 to 32 gigabytes per second per channel, okay? 16 to 32 gigabytes per second of bandwidth per channel, and then you have 8 channels per stack, so then you end up with 128 to 256 gigabytes per second worth of bandwidth per stack. So each of those stacks, or each of those individual, where's the number here? Yeah. Each of these individual things has the capability of getting 256 gigabytes per second worth of memory bandwidth. That's how we get to terabytes, right? Just put a bunch of them on there. Okay, so yeah, for comparison, to sort of think about the high-end GDDR5, so when we switched to HBM from graphics DDR, they were way less wide. Yeah, 384-bit wide versus the many bit wide with many channels that we have with each individual stack for HBM, and the signaling rate was way higher. And so that sort of that's how we got to relatively high bandwidths. And then the AMD part that used the first HBM1 stuff was 1 gigabit per second sampling with HBM, and that was giving you 512 gigabytes per second. And then Ampere, I did update this. I updated this. I added this line. Maybe last year. So Ampere, which was pre-Hopper, 5 stacks, 8 channels each, HBM2, and they're signaling it at 2.4 gigabits per second. So you end up, that's how you get to 1.5 terabit bytes per second in something like an Ampere. And Hopper's just even more and even faster. And that's how it continues to scale. Questions on this? Again, I'm not expecting you to memorize these numbers when you're making your cheat sheet for the exam. Don't write down specific numbers here. I'm just trying to give you a flavor of like how we get to these, numbers. So the other sort of big thing that is very attractive for HBM is energy, because if you know a GPU when you buy it, it consumes hundreds of watts of power. That hundreds of watts of power, some of that's going to compute cores, and a lot of that's going to the memory system. So every modern high performance system is pretty much energy limited at this point. Like you have to design it such that you're using all of the joules that you bring into the chip as efficiently, or the board as efficiently as possible. We could have continued to scale GDDR by increasing frequency if you can get the signaling right. But the ratio, because the signaling was so high, because the frequency was so high, it cost us about 18 picojoules, which, it's small, but that's per bit, okay? Every bit of DRAM you got in the aggregate was costing us 18 picojoules with GDDR5. When the systems moved to HBM, they got essentially a 3x reduction in energy per bit, which means that all that extra power can now go to power more SMs, which means you get more compute throughput, so you get a faster chip, okay? So anything we can do, and this is generally true in all architecture today, to make something more energy efficient without negatively impacting the performance is a performance win. Because you take the extra power that you're saving and you shove it at something else that's going to give you more performance, okay? So this was part of the reason why the move happened, because we had the sort of 3D die stack technology, we got it right. Right now, DRAM is really the only thing we can stack in 3D and in a very reliable way. People have talked about stacking logic too, but that's less mature, let's say. There's certainly not wide commercial product use of that. And it gave us way better energy efficiency and get these massive bandwidths that we need. Now, the downside here is capacity. Okay, now, there is no free lunch. There are a ton of wires coming out of each of these channels. The technology to manufacture these stacks is very specialized. It's very hard to get a whole lot of memory arrays inside the HBM. So that means that when I buy one of these stacks, I'm not actually getting that much capacity, right? So as I add more stacks, I get more channels, I get more bandwidth. You also get more capacity, but the bandwidth scales way better than the capacity does. Okay. So capacity-wise, each channel has its own capacity. So it'll be 1 to 32 gigabits worth of data on each channel. They're scaling this up with the new technologies, but the bottom line is for HBM2, you're only getting 4 gigabytes of data per stack. And you've seen, we're only putting tens of stacks on the PCB, right? So if you want a terabyte of HBM, it's you're gonna have a pie plate for a PCB, right? It's just gonna be like a forest of HBM stacks to try to get you that. That's not gonna work, right? You can't maintain the signaling as the things have to start living further away on your city, right? It's harder and harder for you to actually get the signaling rate of the pins right. There's a reason why this thing is laid out that they're all equidistant from the core itself, right? If I needed to scale this to a terabyte, I would need I don't know what the exact number is. I need tens of these things, 20, 30, maybe 100 of these things. That's not really practical to do and keep the signaling up, okay? And you may ask yourself, well, Professor Rogers, why don't they just make them bigger? This is physics, manufacturing getting in our way, right? Yeah, as an architect, fine, just make the damn thing bigger. Just give me the bandwidth and the capacity. Why not? No, this is why engineering is interesting. Otherwise, we would just fly off the end of the spectrum, right? But actual physical things keep us grounded, so we can't do that. It's very hard to manufacture it at those sizes. It has a lot of bank level parallelism. So you have 8 or 16 banks per channel. Excuse me. And you can have ECC. Okay, so you can put ECC in these things and it costs some overhead. What does ECC stand for? Error correction code. Why would I want error correction code? Bit flips, right? Especially important in computing, less important in machine learning, right? ECC is, so there's 3 things GPUs are sold for today. Graphics. You think ECC matters in graphics? No, it doesn't matter. Like that's part of the markup that if you go to try and buy a GPU that's a G that goes to like a gamer, or you go to try to buy the same architecture with roughly the same specs that goes to something like the government that they're going to put in systems that are trying to run like calculations. The markup's like 2, 3, 4, 5x. One of the biggest differences is the commodity part doesn't have ECC, and the part that they sell to the government has ECC. And they can charge them 5 times more for essentially the same thing because they have ECC. So high performance computing stuff that's doing like physics calculations, think like bomb explosions, think like stuff that's trying to figure out like wind tunnels for new jets. Like you need ECC on these kind of things, okay? Especially if you're gonna like also go put them near a nuclear reactor or something where you have a lot of stray neutrons, maybe like smacking at the chip a lot. Like you really don't want like a 4-hour atomic bomb calculation to like be wrong because a few bits flip somewhere in the middle, right? And you build the wrong bomb or whatever. So ECC is important to try to like in these things that need to be super precise. Graphics. What's going to happen if your bit flips? Your game is actually still going to work fine. It's just going to look weird. And it's only going to look weird on like 1 pixel, maybe. So who cares, right? So we don't need to give them ECC for things like graphics. Machine learning, because the training sort of glosses over a lot of noise, there's good data that it's actually pretty resilient to bit flips, right? Because, we're going down to 8-bit precision, right? Do you really think it matters if one of those flips sometimes? We were at 64 bits because we thought that's what we needed. And that's how we get actually more and more machine learning. We don't call them flops anymore, right? We call them ops, right? Because you can't call it floating point anymore when you go to bits, right? It's just an operation. You want that number to be big, so we just call it op, okay? It doesn't really matter as much because there's not, and maybe it'll matter if we go to 1 bit. If we go all the way down to 1-bit precision on machine learning, then maybe one of those flipping will matter. I don't know. But generally, it doesn't matter all that much. If the algorithms themselves are resilient to these sort of temporal disturbances. So the result is 40 gigabytes HBM2. That's what the Ampere card had for capacity. I think Hopper is 80 gigabytes worth of data. Blackwell will be some constant factor bigger, but not much more. It's using similar technologies. I don't know what it is. I should know, but I don't. And they may not announce it yet, actually. Questions on this? All right. Detailed stuff. Okay, so what are some of the tricks that they added to HBM that don't exist in the other memory technologies? So each individual channel is similar to a channel on a standard DDR interface, except the timings are different. The data interface is actually bidirectional, and it still requires some delay to turn the bus around. Like if I've got a data bus turning the bus around is if I do a load, right, then the memory is giving me the data on the bus. And then if I turn around and do a store, then I have to actually turn the bus around, right? Because the drivers on the memory side were pushing data lines. And then when I want to do a store, the drivers on the memory controller side now need to push those lines. So you got to wait some amount of time. So if your system is constantly cycling between stores and loads, it's bad because you have to wait this turnaround time to turn your data bus around. And so memory controllers are trying to, optimize for that to try to do all the stores in order. This is again why stuff gets reordered. This is why 666 exists, right? Because you're trying to be super aggressive and like do all your writes at once so that we don't have to turn the memory bus around every time. So it still requires this in HBM. Burst length is 2. So 128 bits, that's the actual pins that come out of the thing. That gives you 16 bytes worth of data on the data bus. And then you always do it in 2 cycles of this. That's the burst length. So the minimum access size is 32 bytes. That's why the GPU sector size of the L1 is 32 bytes, because that's the minimum I can get from DRAM. So that's, if I miss and I just miss on one part of a cache line in the GPU, I'm going to go just grab those 32 bytes from DRAM and store it in my caching system. Traditional command sequences, so you still have to activate. You have to activate the rows before you read or write them. You need to pre-charge before another activate. All of these timings, and again, I'm not going to test you on this, but like if you go look at the JDEC doc, like there's all these T somethings, okay, that correspond to the time it takes between, commands to a DRAM or to turning bus around, etc. All of these also exist for HBM, but they're obviously different per channel, right? So you don't have to it doesn't matter what the other channel is doing. You just have to maintain the timing for your individual channel. But all of the same timings exist, and of course their numbers are different than they are for DDR. Again, don't care about, I don't want to get into the guts of the details on that. This is the channel summary. So this is just giving you, an overview of what all the bumps are, what all the pins are that come out of one of these HBM chips. So the micro bumps, so micro bumps are like this. Who's got a good description? Who knows what a micro bump is? Nobody? So it's like, okay. So when you buy like a CPU and you put it in your motherboard, it's usually got like pins, right? Or if you've ever done any embedded system design, like you buy something that's got a pin out, or you buy something that's got surface contacts or whatever, it's like metal that you sort of shove into the board to give the signal to the rest of the board. To try and make sure you have enough of these things, like trying to put many, many pins on one, or even many surface contacts in the sort of traditional sense on one IC is very difficult. So they had to innovate on the IO side to make these things called micro bumps. So they're like very, very small contacts. They're like very, very small pieces of metal that come out from the HBM chip. They go into a specialized socket on the board that connects to these. They call them micro bumps because that's sort of the sexy-ish name they came up with. That allows you to get very dense IO, right? Very dense IO within a very limited chip range. And so that's essentially the pin out of the HBM chip is a micro bump. So data we went over, it had 128, and then it's got a bunch of bits devoted to all these different things, okay? I actually go through what each of these things mean in the video for this class. I'm not going to test you on it. If you're super interested in this, I recommend you go take a look at the HBM video for the class, but I'm not going to belabor each one of these in this lecture here, unless you have questions. Any questions on this? Differential clock. There's a clock enable because differential clock means there's basically 2 pins for the clock. Try to enable fast speeds by basically measuring the distance between, or it's sort of the same thing as a sense amp, right? Trying to measure the change in these two voltages. And then you can turn the clock off if you don't want to suck power from these things. What else here? So one new thing they have is a split command interface. So that means you can do 2 semi-independent commands per channel. So that means that I can do clever things like I opened a row, it's open, and I want to read from that row while I light up another row in the same, potentially in the same, or I think this is in different bank. That's not possible in DDR, okay? In HBM, because they want to be more aggressive, they said that you have to support these commands. So now you can sort of do a bunch of column reads while you're doing row commands on a different bank, okay, in the system to allow you to overlap. So it's sort of like if your memory controller is aggressive, it can open up a row and start reading columns as it's sort of doing a bunch of other independent stuff with the other banks in the system. I don't think they allow this on a per bank basis, but I'd have to double check. Okay, why do they want to provide separate row commands? You want to get 100% column bandwidth, ideally, because you want to use all of the stuff that you've opened up the column. It simplifies the memory controller because now it can sort of issue these things independently. It doesn't always have to go, in this order. And it could potentially give you better performance because you can start the activation earlier and not delay additional reads and writes. You still, however, have to enforce this rule of activation, rewrite, and then pre-charge, all those timings that are associated with that. There really is nothing fundamentally different about HBM, right? It's still these sort of cells that are reading out rows. There's just many more of them stacked on top of each other. They have single bank refresh. So in current DRAM, remember the refresh? I said refresh sucks, right? When you have to go to when you have to basically go and initiate essentially read commands again to every line to make sure that the data doesn't disappear because of leakage from the trench capacitors. Again, the technology is similar, right? It's still just capacitance that's holding the bit charge in these HBMs. So they still have to be refreshed, but you can actually do a single bank refresh. In traditional DDRs, when you said refresh, you had to refresh all the banks in the chip. Okay, even if it was like, so this sort of like intermittent refresh was very difficult to do in commodity systems. You can do it more easily with HBM because they allow for this. And right. So yeah, so the current ones, refresh commands require all banks to be closed. It's about, it's one refresh command every 3 microseconds. That can suck away bandwidth. And as you get bigger, of course, that the downside goes up. And so you can sort of, use your memory controller to do some clever things to overlap the activation and pre-charge, refresh single banks, etc. How much does all of this matter? I haven't seen a great study that has shown like what the difference is. I think that a lot of this is driven by, so JDEC is the standards committee. It has 2 inputs, right? One input is the memory companies, and the other input is the memory companies' consumers. And so the memory companies' consumers, like NVIDIA and AMD, are pushing for these kinds of things so they can build better memory controllers to maybe differentiate their memory controller versus the competition. The memory people are like, no, like don't make us do more stuff. So there's like this tension between, memory companies not necessarily wanting to specialize too much, and then the other companies wanting to give some level of programmability, and that's sort of playing out in how HBM has been developed and continues to evolve. Support CCC as a standard. Again, you don't actually need to do it, but it's possible to do. There's not really much that's interesting here. Anything else? Let's go back. Right. So you can do some self-refresh with HBM. This is kind of like a laundry list of like, this is all the kind of semi-interesting things they added for HBM. So your refresh rate that you actually need to maintain is affected by temperature. Right? The harder the chip is, the more you'll have to potentially refresh it. If it's cooler, it'll hold its charge longer. And so you actually have a temperature sensor that you can read, right? So that's not standard in traditional just DDR chips, but HBM chips say you have to support this. So that means the memory controller can send a signal to the chip that says, give me your temperature. Then the memory controller can be like, oh, well, you're cool. I can wait a little bit longer before my refresh. Whereas in previous generations, you couldn't do this. There's also this kind of interesting bus inversion thing. So this is kind of interesting. I'll explain in some depth at the beginning of next lecture, but the basic idea is I want to switch signals less frequently, because the more I switch the data pins, the more energy you consume. So this is just the data, right? So who knows what it is? It's like ones and zeros that represent the actual data itself. Ideally, if you could somehow have some kind of quasi compression technique to try to switch them less frequently, to say that I want to interpret, I'm going to send you 00110. I want you to interpret that as, in some instances, it's actually 00110. In some instances, I want you to invert the bits and interpret the zeros as ones and ones as zeros. And if I'm a clever memory controller, I can basically use this extra inversion signal that you get on collections of bits to limit the number of times I transition each of the data bits based on the address, the data that's currently on the bus and the data that's going on the bus. And they added this explicitly in the spec for HBM to try to just limit the dynamic energy consumed when you're sending signals across. HBM2 is sort of evolution of HBM. So things get wide, things get faster, you get higher bandwidth. There's these things called pseudo channels. Yeah, I'll cover this in a bit more depth at the beginning of next lecture. And then we'll just finish off with the HBM slide deck. Any other questions here? I went through this part a little bit fast. I'll try and go through the HBM details a little bit better at the beginning of next lecture. I realize I sort of skipped a bunch of this. Okay, that's it. I'll see you guys on Thursday. Thank you.